Hi to everyone. Thank you for joining us, and big thanks to Robert as well, because we've been trying to get this presentation since last year.
Yeah, and we're so stoked that Shruti reached out to us.
Yes.
Zaneta and I are both quite passionate about sustainability, but I think we can't hold a candle to Shruti over there. So
Right.
we're
Yes. Thank you so much for joining us.
lucky she's willing to give us this presentation, and knows a colleague of mine up in the Smith Group San Francisco office. She's been working closely with him and pushing all the sustainability aspects of the recently completed UCSF Wheel Neurosciences building. And she's gathered quite a few fun case studies to look at energy and energy consumption at numerous scales, from building and up to the energy grid. So without further ado, I want to hand it over to Shruti Kasarikar. And Shruti, I think it might be fun if you share what got you down your career path.
Absolutely, would love to. Thank you so much for having me. I am delighted to be talking about my passion here, which is the future of carbon neutral design. But like Robert requested, I am also happy to share how I got started here. And this is sustainability is not something that I found my way into. I think it was quite deliberate, which I did not know going into undergraduate school that would be the case. So I did my undergraduate degree in architecture in India. And while doing so, I think a few years into it, I think I started developing this sense of what design means for me. And I think for me, design meant that I have to find meaning. As a result, for my thesis, I was preparing my design, and without any sort of like background or no one like nudging me into it, I ended up creating all these calculations for cutoff angles for shading and a natural ventilation rule of thumbs, and U values and R values for roof and wall assemblies. And I presented that to my thesis advisor, who said that this isn't an architectural design, this is a scientific solution to architecture, to which I challenged and said that I will make a career out of it, and I will show you that this is an integral part of the design. And I continue to think that that is how it should be, and that is how architecture should be, and here I am. So that's my little story of being in sustainability, and I cannot be excited about the times that we are in, because right now is the time for us to have an impact and make a difference, and make a difference at a scale that architecture has probably not seen before. So without further ado, I will jump right in. I think I paused this slide for some reason. 1 second. Okay, there you go. So a little bit about Atelier 10. We are a group of environmental designers, that's what we call ourselves, who are focused on delivering sustainability, and the definition of sustainability changes for us for every project. We are a group of people who have various backgrounds, from architecture to urban ecology to material toxicity, mechanical engineering, electrical engineering, lighting design, master planning. So all different angles here come together, and I think we share this passion about making a difference in the built environment at any and every scale, and that's what we are. Our basic principle around our practice is to have buildings do more, to have the landscape, anything that we sort of like build, do more and find meaning into it. We go back to the first principles very regularly. I think that's who we are. So we go back to the basics, try to look at the physics and the science behind it, and try to provide solutions and strategies around that. we love to work with architects, and a lot of us are architects by training. So we naturally speak that language, and we absolutely value design and love to work in an integrated design process and come up with solutions that are not just created by us, but that are design solutions that have been created by an integrated team. And one of the things that we have developed over years is that we remain very pragmatic. We are very practical. We understand what it takes to deliver architecture, and we think that solutions should be pragmatic for them to become real and for us to learn from them and to move forward. So our practice is very pragmatic. We do all of this through an umbrella of services. Environmental design, facade optimization, you can see this big list here. And essentially, our services have been developed because we find it very often on projects that the needs are different, the client is different, and the solution is different. So it isn't one answer for all the projects. It is a tailored and a unique and a custom answer for different projects. So we use, whether it is environmental design or facade optimization, or whether it is energy analysis, benchmarking, it depends on what the project needs and criteria is, and we'll bring in that expertise and that menu to the table to deliver sustainability. We remain a pretty small firm. We are around 100 people in the United States, and we have more than 11 offices all around the world. Because we are still quite small in size, we work across all the offices quite regularly. What that lets us do is we have experience in different climate zones for different typologies in different cultures, and we regularly share resources and projects across our offices. So that's our introduction. I wanted to give you this context to tell you where we are coming from and why we care about this. And essentially what you're going to see through this presentation is that our viewpoint has been developed by working on similar topics and similar questions for years and years, again and again, trying to answer the next thing on the next project. So you're going to see that approach here that I share through multiple case studies where we've tackled a few issues, and then the next project allows us to push that even further. So we continue that journey. So why do we care about carbon? So again, like setting the stage here for carbon emissions. And most of you are, I'm pretty sure, are very well aware of the recent news on climate change. And honestly, for us as a practice, in 2018, I think was quite a defining moment for us. Until then, we were talking about climate change, we were talking about carbon emissions as a thing that we all should be doing on our projects, and that's the lens that we should have to look at our buildings. However, in 2018, as you may have heard, the scientific community basically published the report, the IPCC report, that stated that the global warming is likely to reach 1.5 degrees Celsius threshold between 2030 and 2052. 2030 is within a striking distance already. It is this decade. And 2052 is basically, that's where all our projects are going to be still alive and very functioning. So everything that we do right now, everything that we will be designing here on forward is going to see the effects of climate change. And so that was like a really a shocking and a big realization for us that we need to tackle climate change faster than we had a thought before. And we need to do it right now. And we need to take a look at what impact climate change or carbon emissions have on our projects in terms of order of magnitude, and what can we do about it right away. So with that, we also see that local jurisdictions and codes and standards have also started to evolve based on this information. So in September of 2018, California SB 100 went live. And essentially what it said was that all electricity in California was to be carbon-free by 2045. It would be majoritarily be free by carbon-free by 2030. Again, this is within the next few years, and this is a huge opportunity for buildings. And this is not just in California. We see this change all around the world, definitely in all jurisdictions in the United States. Places like New York City are going even a step further by saying that they want to have 100% renewable electricity by 2040. So that's even sooner than California. The other place where we think or where we see the codes are going is the embodied carbon emissions, which is very close to heart and also where architects can do a lot of change. And California AB 262 requires that state agencies consider embodied carbon emissions for materials like steel and glass when contracting for state-funded infrastructure projects. It is only a matter of time that this language gets translated into local codes like Cal Green, or even the prerequisites for LEED, which eventually become the code for local jurisdictions. So I think that embodied carbon is something that the built industry is just beginning to tackle. I don't think the time is very far that we will be doing so from a base minimum code perspective also. So that's where the industry is in general going. So when we think about decarbonization and decarbonization within the context of the built environment, there is so much that we as designers can tackle. And we've always talked about energy conservation for the past many years now. I think the new information that is coming to light as a result of some of these mandates from local utilities and states, which is that electricity is getting cleaner, which means that our energy sources are getting cleaner. And we need to take a new look at how to design buildings to take advantage of that. In addition to that, embodied carbon of materials I just mentioned, so that remains a significant topic for designers to influence. In addition to that, there are so many areas and there are so many avenues through which designers can influence the carbon emissions of projects. The built industry isn't recognizing formally some of these. Doesn't mean that we shouldn't be aware of them and we shouldn't be tackling them, but some topics like refrigerants, waste that is created through buildings, water, transportation, are key criteria that are going to influence the overall carbon emissions of any project. And then there's one place where you're not, or the buildings are not emitting carbon into the environment, and rather they're absorbing carbon through the environment, which is landscape. Especially for projects that have a high percentage of open space or have a high opportunity for green spaces, there is a huge advantage to look at these opportunities as carbon sequestration opportunities, to not just emit carbon into the atmosphere, but in fact to absorb it back and to help your project be carbon negative. So with this boundary of decarbonization keeps on expanding as we find new things and new opportunities. In this particular presentation, I'm going to be talking about the energy sources and the embodied carbon of materials as two topics to dive in and to tangibly understand what we can do right now to make the carbon emissions associated with these lower. So I think the way my presentation is set up is I have two sections where I introduce these two topics, embodied carbon emissions and operational carbon emissions. And then I have a few case studies to illustrate how through design we can achieve these goals. So I'll go through the embodied carbon emissions section first. And also, I forgot to mention, but if you feel that a question is going to be an important part of this discussion while we are in it, please feel free to say so in the chat. I'm happy to take questions or a discussion while we are going through that presentation as well. So a lot of you may already know what embodied carbon is for buildings, but for those of you who may be new to this world, here's a refresher. So for every construction project, there are three cycles. One is the extraction, assembly, and the transportation cycle for materials. Then the materials get installed into buildings and the building gets utilized. That's the operations piece. And during that time period, there may be renovations that are happening in the building. That's the renovation piece. After the useful life, the materials are discarded, and that's the disposal piece. So for each of these stages of the material life, there is carbon that is consumed in the activities associated with these stages. In general, extraction, assembly, and transportation are extremely energy intensive. Building renovation and operations of building, once the material is in place, it is in place and it's not actively emitting materials as long as we don't keep on renovating the project. And then disposal becomes very carbon intensive if the materials are not designed for reuse or for recycling. So understanding how these life stages of materials come together and how they affect the carbon emissions of the building is what is called as the embodied carbon life cycle. So how much does this matter? And is it a big deal? Should we care about it? So here's a characterization of, on the left, what you see is a 60-year time period of carbon emissions. And what you see here, blue is all operational carbon emissions, which means it's the energy that is utilized in the building. And the warmer color scheme is the embodied carbon emissions. So when you're looking at a 60-year time period of a building, embodied carbon emissions can be, this is like a very average building. It can be about 20% of your overall carbon emissions. However, you make that time period shorter. So here's the same building for a 20-year time span. And suddenly the embodied carbon emissions become a much bigger chunk of the pie. Now take this information and just revisit what we saw in terms of this decade being really important for minimizing the carbon emissions to keep the 1.5 Celsius temperature rise in control. So because embodied carbon emissions get locked right now, you can't do anything about it after a decision about a material is made. You can't change that. It gets locked in for the life of the project. Those emissions mean a lot for right now and for this decade. So embodied carbon emissions from a time of use perspective, from a time value perspective, are extremely important because those decisions cannot be undone. Operational carbon emissions, on the other hand, are slightly different. Operational carbon emissions you can change tomorrow by doing a energy audit of the project or by changing the systems in the project. You can perhaps change that a little bit. It is very hard to tackle embodied carbon emissions after the design decisions have been made. And therefore, it's more important for us to do that thinking while we are designing the project. So a few years ago, and I'll tell you what, like for the entire time that I've been in this industry, we've been trying to tackle embodied carbon of materials, and there hadn't been a standard that we can utilize, which would allow us to do an apple-to-apple comparison of projects. And that was a huge limitation. A few years ago in Europe, really important body of work happened, which is a few people came together and they decided that we need to create standards to measure the carbon emissions associated with these various stages. And here's a process that they came up with, which has now become a standard for evaluating embodied carbon emissions for all projects in the world. So what that standard or what that process involves is looking at the product stage, the construction process stage, then the use stage, the end of life stage. And all of this together then becomes your building life cycle. And now that we have this process, we can utilize it to compare to completely different materials as long as we are representing all the right stages. So that was a really useful piece of work. And what that has now translated into is various agencies and various organizations taking that and creating a boundary for projects for assessing embodied carbon. So you may have noticed that the current version or the latest version of LEED, which is LEED version 4 and 4.1, has started to acknowledge embodied carbon emissions. And just to put things into perspective, here's the LEED scope. So LEED, when it says it cares about embodied carbon emissions, it cares about the structure and the enclosure. Those are the two categories that LEED has said that we would like to have projects evaluate. We think that carbon emissions, when we are looking at it, we should at least be looking at the structure and the enclosure, plus the interiors and the systems. And that gives us a full picture, which we call as the complete building. And then again, like the decarbonization chart that I had earlier, that boundary can, that boundary can be expanded to include site, landscape, and everything that we as designers touch through our project site boundary. So if you care about LEED and if you want to know how this impacts, LEED version 4.1 awards up to 3 points for completing an LCA, which is the process that I described earlier, and by reducing the embodied carbon emissions of structure and enclosure, which is what LEED cares about, by 10%. And three points is a pretty big deal for projects that have high aspirations. There are other certifications that have now started acknowledging embodied carbon emissions, and that one of them is the AIALA Zero Carbon Certification, which requires that projects be net zero energy, so that's the operational carbon emissions, and then it also reduce embodied carbon emissions of the foundation, structure, and enclosure by 10%, and disclose and offset the remainder of embodied carbon emissions. So it is a little bit more stricter than just LEED, which caps all the efforts at reducing the carbon emissions by 10%. ILFI would like the projects to also offset the remainder of the carbon emissions. So what can you as designers be doing on your projects? And oftentimes, the challenge is that when you are in early phase of projects, when you are in concept and schematic design, we don't have a very good understanding of exactly what material quantities we have for the structure and for the enclosure. We don't have that level of detail. So if we don't have that level of detail, how can we meaningfully still do progress and make the right decisions on projects? So here's an example of how you can do that. What can happen in early phases of projects is a apple-to-apple comparison of material types or products within the same group. So for example, here is a comparison of different configurations of concrete that can be used for the project And it is doing a relative comparison of those concrete mixes to see which configuration results in the lowest greenhouse gas emissions. Similarly here, what you are looking at is a comparison of different types of insulation. So what you see here is this is light density mineral wool insulation, and this is XPS insulation. And then here's a variety of polyiso insulation, again, another mineral, heavy density mineral wool, and fiberglass insulation. So by doing a comparison of just insulation type in terms of their intensities can tell you which material is better compared to the others. And that can still have a huge influence on how your assemblies are going to be designed and how much space and detail you need to include in that assembly design. So these types of early design comparisons are really useful to be able to make the big picture decisions in the right way. And then eventually that can be translated into a whole building LCA from like design development phase and forward. And here are two other examples that do a similar comparison, showing which type of facade system or which type of shading system is better than the other. And here in this particular graph, the line at the top is the most carbon intensive, the line at the bottom is the least carbon intensive. And this is doing comparisons for similar systems. Another way to tackle embodied carbon emissions is to look at a material category, and we know just by sheer volumes that steel and concrete are always going to be always going to have extremely high embodied carbon emissions. So those are great starting points for us to do a deep dive into what can we do about concrete. And as you know, probably better than me, that concrete is not one mix for the entire project. The mix design changes depending on the application. And the opportunities change also depending on the application. And there are so many considerations like the strength of the concrete, the curing time, the appearance of the concrete that determine what mix will ultimately get designed. So here's a project where we looked at all the mixes in the project that were considered. And for each of those mixes, we worked with the structural engineers and with the architects and with the concrete supplier to figure out what type of cement replacement was possible for that particular application by considering the strength, the curing time, and the appearance criteria. And just based on that, you can begin to see here that the opportunity for reduction is pretty huge. As an average, we see that within the family of concretes, there is an opportunity to reduce the embodied carbon emissions by 30% if the mixes are properly designed with that criteria in mind. And then another one, which again allows us to do a comparison early on, is interiors. So interiors is something that for the longest time was ignored because, you know, when you have concrete and steel to deal with, who cares about interior products? And also they, you know, just because they're, you know, smaller in volume and they are, there is a variety of them. That was the traditional or the old way of thinking. What we have found through some projects is that interior products by themselves can be very effective in reducing carbon emissions if you know which ones are typically easy to be replaced. And so what we did for a project is to look at the various types of interior finishes that were utilized on the project and to come up with the carbon emissions profile for each of them, what we realized very quickly is that products like carpet tile and paints are extremely carbon intensive. And this has given us a pretty good sense of the biggest culprits from like carbon emissions perspective in typical interior products that can still be prioritized. And just by tackling those top 3 or 4 materials, you can get reductions as big as 10% on your interior carbon emissions, which is quite significant. So we continue to find that carpet tile, interior paints especially, I think is something to really focus on, because not only are they quite carbon intensive, if not properly selected, but they also have pretty significant health impacts. And here's one more comparison, and this is where we get into figuring out the decisions that we are making for carbon emissions related to materials. If they have a function, how can we justify that material in a project? So allow me to explain this a little bit better. So for a project, when we were looking at aluminum exterior shading, we were curious to understand that we want exterior shading for the project because that allows us to reduce the cooling load in the building and therefore the operational carbon emissions. Therefore, we want exterior shading for the project. But how can we design that aluminum exterior shading so that it can pay back very quickly? And it would pay back very quickly by reducing the cooling load in the building. So what you see here on the left here is a comparison of various types of aluminums. So this is just in the family of aluminums. Depending on where it is sourced and what is the manufacturing process, the carbon emissions associated or the global warming potential associated with aluminum can be extremely different. And then once we basically arrive at the type of aluminum that we want to be selecting on a project, then the finesse is how to design that exterior shading with the least amount of material possible, while also providing the beneficial shading so that it can do its job and we can recover the carbon emissions associated with that material through reduced cooling in the building. And what we found is that when a project is properly designed, in this case, it was an exterior shading system with an optimized material quantity, we were able to pay off that material investment in as short as 3 years. And then no embodied carbon conversation can be complete without existing buildings. We love the opportunities that existing buildings present when it comes to preserving the structure and the enclosure where possible and still redesigning the buildings to be beautiful and habitable. And here's an example. This is the Cal State LA Physical Science Building Renovation Project. And using this particular project as an example, we looked at what is the amount of carbon that can be saved by saving buildings and by renovating them instead of just demoing them and constructing new buildings in their place. So what you're seeing here is that if this building was demoed and just reconstructed, then this would be the profile of the carbon emissions. And this is both its operational as well as its embodied carbon emissions together. By just saving the building enclosure, the building structure, in this particular case, we were able to reduce carbon emissions of this project by 29%, so that one single move reduces the carbon emissions by about 30%. And then in that process, by renovating it, also making it more efficient, reduce the carbon emissions by a total of around 50%. So that's quite significant, just the fact that you're taking an existing building where the embodied carbon is already locked in and then making it better by reducing its operational profile. You can reduce the carbon emissions of that building by 50%. And then the one place that I mentioned is landscape, where we can have a positive difference. And a couple of years ago, we partnered with CMG architects and helped them create a tool called the Pathfinder Tool. This tool is available for everyone to use. So you can use this location to access it. And what it allows you to do, especially for projects that have a very big open space component or a landscape component, it allows you to figure out the role of landscape in sequestering carbon. And it gives you some metrics on the type of landscape that can be beneficial towards it, and it allows you to quantify it. So please feel free to use it and experiment with it, and then reach out to us if you have any questions or if you have any suggestions. We'll be happy to take them. So that was an overview of embodied carbon emissions. Now I'm going to move on to the operational carbon emissions. And the story about operational carbon emissions is only renewed and is only possible to be told when we take a look at the grid and the state of the grid. And my viewpoint here is very California specific here, so this is very relevant to us. So a couple of years ago, we also decided that we wanted to really take a look at and reevaluate the way we are talking about energy use and greenhouse gas emissions and the connection between these two. So for all these years that I have been in the field, we've been wanting to talk about carbon emissions. And somehow we kept on getting dragged into site energy or energy cost, or in California, source energy, all as a substitute for carbon emissions, while never talking about carbon emissions directly. And for you to understand the difference between these four, site energy, so if this box is a building, site energy would be the energy that would be measured right at the boundary of that building. Energy cost is some sort of proxy that is paid at the meter here at your building, but really that is all determined by the utilities and how they operate their plants. So it has less to do with carbon emissions or your energy use and more to do with how the rates and the cost structure works at the utility companies. Now, source energy was the closest that came to carbon emissions, and that was California's way of getting closer to carbon emissions. But it still made you measure energy at your site and then convert it into a source metric. And then carbon emissions is what we all should be caring about, which is the carbon that is emitted into the atmosphere. And so we are very glad now that the industry is talking about carbon emissions. That's what matters. And the rest of it was all proxy. And I'm glad that we are now ultimately talking about carbon emissions. So how and why is this different? So allow me to introduce this concept to you. Here's a typical energy use profile for a building that you may be familiar with. On the left scale is a full day from hour 1 to 24. And on here top is January through December. So this is your annual profile. And what you see here, which is very typical for California, is that summers are pretty hot. The rest of the year is pretty warm. Nights are nice and cool. And that is reflected in how buildings utilize energy. So red is lots of energy, yellow is medium energy, green is low energy. Now, if you look at how the rate structures and how the utilities look at cost, it sort of reflects how energy is utilized. So typically, the costs of electricity are high during the summertime. They are low during the shoulder season and early hours. And then they are very low during the nighttime. But take a look at this profile here, which is carbon emissions. It does not reflect your building's energy use, nor does it reflect the cost of energy. It has its own profile, and that's because the power plants, the way they are operated and which power plants are operated is not based on how the buildings are using energy. They're based on how the grid works. And so the grid fires up, or the power plants that utilize coal, for instance, are fired up at certain times of the year. That has nothing to do with when we are designing energy efficiency measures in our building. They're completely different. And so we as designers need to understand how the carbon emission profiles are being controlled to be able to really design measures in a building that can respond to this profile and not this profile. So how do we do that? So previously, you might remember, or you might still be doing it. We build an energy model for a project. Then we multiply to that energy number the greenhouse gas emissions factors that we get either from the US as a nation or from a local utility or a state average. There are so many sources. And then that gave us our greenhouse gas emissions.
Hey, Shruti, if
Yes.
you don't mind if I interrupt, if you go back one slide.
Yeah.
I'm just curious, 2 questions for the image on the far right. One is, is there some sort of relationship that you see between the downstream usage and the relationship with how the grid fires up? And then 2, is that graphic on the right, this is sort of for all of California, or, and I imagine that would change based upon where you are and what grid resources are available.
Perfect. Yes. So I'll answer your second question first, and then the first question after that. So it changes, and I think that's exactly where I was going. So let me just go there 1 second, sorry. Okay. So yes, it changes depending on your grid region. And the grid regions are not the same as the state boundaries. They're not the same as any boundaries, really. They are their own boundaries. And they are called as the balancing authorities or the ISOs. And so for any project, rather than noting that your project is in LA or in San Francisco, when it comes to operational carbon emissions, what we should be utilizing for our projects is which grid region are we in? And so for San Francisco and for a lot of LA region too, we are in the CAISO, or CALISO is also what it is called, region. And so the carbon emissions profile associated with that grid region is what we need to understand to be able to make meaningful decisions downstream on our projects. And the only exception to that, by the way, is Texas, which the entire state has its own, is also its own grid region. And that was, if you remember last winter, when the entire grid basically went down, that was, the entire state was affected, and that was all over in the news. And that was because the entire state is its own grid region. That's the only exception is that. But the rest of the country is all intermingled grid. And then your second question, which is how do we influence our decisions and our strategies in the buildings to be responding to these, is exactly what I want to talk about through the case studies on how we can do that. A lot of those, the short of that is a lot of those do go to the first principles of how can we create buildings that consume less energy in the first place, so that we don't really care whether it is green or whether it is yellow or whether it is red. And one of the reasons why that is important is because the grid profile is going to continue to change as more and more renewables get fed into the grid. So we are not just designing buildings for a static profile, we are designing buildings for an ever-changing grid profile. So to sort of hedge our bets around something that we do not know exactly how it is going to turn out, the best thing to do is to go to the first principles and consume as little as you can. So I think we still believe that that's like an excellent starting point, and we should be challenging that as much as we can. And then the second one is there are some really intelligent and interesting ways to adapt to this changing nature of the grid, which is what I'm going to show through some strategies. And I think that's where buildings need to go for future, on how do you, when you don't know whether this red is tomorrow going to show up somewhere here, how do you design strategies that allow you to adapt to that? So, like we were just discussing, the new way to factor into our conversation is not just how much energy that we are using. We should definitely be talking about that, but not just that. It is also when we are using energy and how that relates to the carbon emissions profile. So how much, when, and then looking for the right grid emissions factor through the balancing authority that you are in will give you your greenhouse gas emissions. So if you're interested in more of this, we've written a whole white paper that talks about when and how and goes into a deeper dive of this. It's called The Future of Carbon Neutral Design also. And it's free for all. It details a full methodology on how this calculation should be done. And then we love to talk about it. So feel free to reach out to us. Feel free to reach out to me if you have any questions, and I'll be more than happy to answer them today or at any later date. So the first step that we are seeing how the built industry is responding to this changing nature of the electric grid is by electrifying buildings. So there are several REACH codes now in California that local jurisdictions have adopted that have banned natural gas and that are expected to now continue to ban natural gas for eternity. What that means is that previously, domestic hot water, space heating, food service and cooking, and laundry were typically fed by natural gas. And now those end users are being converted to electricity, and we need to begin to accommodate that electrification into our building design. Depending on where you are in the United States, we see different flavors of electrification. Some are all electric HVAC, some are completely all electric. Some have developed a path to all electric, knowing that this is coming up in the future. Some have a hybrid approach where they have a methodology to swap specific pieces of equipment. Some are becoming electric ready. and some are putting it all on the central plant and keeping the building systems simple. So there are different flavors of electrification, and oftentimes it is hard to understand for designers on where all of this is coming from. But just know that there is no one answer. Depending on the client need, I think the electrification or getting ready for this changing grid can take many forms. And there are a lot of options that can be pursued before settling into a decision that electrification or this taking advantage of a cleaner grid is not a thing for your building. So let me now run through some case studies to show how we've either gone to the basic principles to think through some of these critical issues and embed them into design, and then also some of the newer upcoming technologies that talk about flexibility and responding to an ever-changing grid. So I think this is the slide that I wanted to talk about to answer your question, Robert, which was, we still believe that the basics of looking at passive systems, then going for active systems, then tackling the plant, then renewables is the right methodology to tackle even buildings that have a changing grid. So that continues to be our methodology. I think the building skin plays a very interesting and important role in all of this. And just hold on for 1 second. It's getting pretty dark here. I'm going to turn on the light. Sorry, my apologies. 1 second. Okay, sorry about that. So and the building skin has multiple roles, and we want the carbon story to be integrated into these roles together. And so that we are not just designing for carbon emissions, but we are also designing for the occupants and for the experience that the building skin is supposed to provide. So daylight access, views, visual comfort, and the peak solar control that sort of like puts all these things together, along with the carbon drivers that I showed you through some of the comparisons that we've done together, form the criteria for designers for the building skin. So let me show you an example that recently got built and is now operational. It's the Uber headquarters project in San Francisco. This project, so we were brought onto this project actually pretty late compared to when we get involved. And you know, this is for those of you who haven't seen or heard about this project, it is an office building project by Shop Architects, and it is located in San Francisco. It is about 450,000 square feet of office space. And as you can see here, it is split between two buildings. This is an 11-story building, and this is a 6-story building. And the whole idea, which came from the then Uber CEO, was to essentially have a glass box. That was literally the vision for the project, to have a glass box. That was the client brief. And when we started working on this with Shop Architects, both Shop Architects as well as us, we realized pretty quickly that it is going to be not just difficult to pass the energy code in San Francisco for this building, but also conditioning a whole glass box is not a great idea. So our environmental approach and our entire carbon approach for this project was to figure out a strategy that would not be the default solution, which is the client asked for a glassy building, we got to condition the glassy building. So what we came up with, and this was actually part of the design itself, was what you see here in red is the entire volume of both of these buildings combined and connected that was supposed to be this really transparent, easy to see, easy to access type of space that is called as the Solarium. And we quickly realized that that is actually a great opportunity, because as you can see here, this entire space is on the building perimeter, which means that this is the space that is going to get hit by that intense solar radiation, and it is a glass box. So we thought that this is a great opportunity to figure out if this entire space criteria can be developed in a way so that it can become more open, become more integrated with the outside than integrating it with the inside, and thereby potentially getting rid of conditioning for this space altogether. So here's a rendering, which, by the way, it looks, the actual pictures and the actual building looks exactly like this. This is that in-between space, which is called the Solarium. Here's the outside, and then the interior is, which is the office space, is protected by this in-between Solarium. So as you can imagine, what we our focus quickly shifted on, how do we design this space to become this in-between space where the experience, the human experience, can be controlled, as well as it doesn't require conditioning. So that required us to do a deep dive into thermal comfort and how humans would experience the space, and what would be the factors that would affect human thermal comfort. And it came down to a few criteria which were related to the environmental aspects, which are air temperature, mean radiant temperature, air velocity, and humidity. So what we did was we took that space and we ran analysis to understand what happened if we treated this entire space as a traditional closed off box. What happened if we added operable windows and shading in specific areas and designed in a specific way? And what happened if we integrated some very minimal but intentional cooling that allows us to manipulate the environmental factors associated with thermal comfort that would then allow us to not condition this entire space? So what we came up with essentially is a combination of operable windows and shading criteria for this space that allowed the air to move in certain direction, that prioritized the opening of the facade in a particular way, in a certain sequence, responding to the external conditions. And the fundamental concept of this space became that it is an in-between space that does not have the thermal expectation of an indoor space. So I think that defining that criteria, that it is not an indoor conditioned space, it is an in-between space. How do we program this space for it to succeed as an in-between space? And how do we create the thermal expectations for the occupants so that they do not expect interior conditions in this space? Through the combination of these strategies, allowed us to design this entire continuous space as an unconditioned space. So here's a comparison then to the overall energy used to give you a sense of how impactful that was. If the project had taken the route of conditioning the glass box as is, this would have been the extent of the conditioning energy. And once we remove that conditioning element altogether, the saving is about 65% for this for the Solarium. So it goes back to basically saying that the strategy here was to not tag on a lot of intelligence really into the building in terms of just, coming up with a solution that conditions the space effectively. We went to the drawing board with a more fundamental concept of how can we just get rid of conditioning in the first place and come up with a program and a design that allows us to do so. The next example that I have, and if this was not clear through the Uber case study, I just wanted to make a point. So this case study sort of like talks about how to effectively go back to the basics and deal and design the facade to enable passive strategies, which then avoid emitting carbon emissions in the first place. The second example is right now in construction in LA. It is called Horton Plaza, and we've been working with Rios on this. This is a project about 700,000 square feet in LA, and this is, I'm sure you know this better than me, but this is an existing shopping mall that is being converted into an office space. Pretty high aspirations in terms of LEED, WELL, and also a new benchmarking system for you if you haven't heard of it. It's called Wired Platinum Rating or Wired System. And this is so in contrast to some of the projects that you may have worked on. This project is a developer-led project, and so the criteria for the design of the facade and the role of the facade was quite different. Here, the first cost was a extremely important criteria for the project. And we knew that the entire enclosure design and the effectiveness of that enclosure to control carbon emissions and to create the experience that we want is going to be highly dependent on that first cost. So what we did in the very beginning was to start by looking at here I have both the west facade on as the lower row, and the south facade is the upper row. And we looked at the combination of exterior shading and glazing specification, the combination of those two to identify what kind of facade options are possible within the cost model that is available. So here were some of the options that were discussed. Next, what we were interested in looking at were two set of criteria. And this is an example of where we've used facade as a avenue to design for both experience as well as for reduced carbon emissions. So what you see here is the type of analysis that was done on those facade options that allow us to hone in on the experience. So on the right, what you see is the impact of the facade on the daylight distribution on the floor plate. So it's a pretty thick floor plate, or pretty wide floor plate. And what you see here, pink is the overlit area, blue is the underlit area, and then white is what we call as the usable daylight. So this is an annual performance that is overlaid onto the floor plate to give a sense of what impact the facade is having in doing both, bringing in daylight as further into the floor plate as possible, as well as protecting the immediate perimeter from extreme light. And then in combination with that, I think an important way to look at facades is it's very hard to imagine how users are going to end up utilizing that perimeter space when you look at a map on a floor, because users don't experience space in terms of an annualized result, right? Like we are experiencing the conditions right now, and that is affecting how you're going to behave in the space. So we do what we call as a point in time analysis that tell us for a typical for either the south or the west orientation, if the desks are laid out in a certain way, how a occupant will be able to actually experience the space. So what you're seeing here is a fisheye rendering that is showing you where the ball of the sun would cause visual discomfort, and how, and this is basically the west facade, and how, despite best intentions, that is going to lead the occupants to draw the shades down, and the glassy facade is not going to matter at that point. You're also going to compromise on the daylight axis for the rest of the floor plate. So we use visualizations for this to illustrate how on the west or on the south during certain times of the day, based on a certain layout, how occupants might actually visualize the space and experience the space, and what their behavior is going to be as a result of that. And this is basically just a rendering that that converts this experience into a glare metric, which is called as the direct glare potential, and tells you whether this is like too much glare that is going to cause visual discomfort or not. Here's another example for West, where this is showing when the blinds are down. So I'm just going to like go back and forth between these just very quickly to show you that here's the ball of the sun. Here it sort of shows that, oh, the floor plate is quite beautifully lit because there's all white here, and a little bit of the area is pink. This is a well daylit space, but this is what the occupants are actually going to experience. And then they are going to do this, which is draw the blinds down so that they can get a good environment. And it is going to result in this, basically, which is that no daylight into the space. So I think what this illustrates is combining occupant experience into facade design to inform ultimately the carbon emissions, as well as how the success of the experience for the space. So taking this, going back to some of the options that I had shared with you earlier, we developed these sets of criteria, which is taking the types of metrics that are important for a developer, the types of metric that are important for an architect, and the types of metric that are important for us together to come up with almost like this, like red, green, and yellow sort of a bar that allows us to see which facade system would give us the maximum benefit. So the criteria here is to maximize the desk space, to have hours without shade or tint, visual comfort, thermal comfort, daylight potential, a simplified mechanical potential, because the facade and the solar radiation impacts the size of the mechanical system, the color rendering, and clear views out. So it is a complex set of criteria. It's not just carbon emissions. It is a complex set of criteria, but it is getting us to the ultimate goal of being able to both deliver on experience as well as carbon emissions. And then here's the beautiful facade system that was developed as a result. And something to note here, that I want to say that the window to wall ratio for this facade system is, I don't think it is more than 50%. So we worked on that aspect also quite a bit. Again, going back to those first principles, that was one of the criteria in our mind also, that yes, we want, even as a developer project, we want to prioritize glass, but we want to prioritize glass where it matters. And the rest of it we want is as opaque as possible. And we were able to deliver this within the cost budget, serving the experience criteria as well as the carbon emissions criteria. Here's the building rendering, and here's my favorite showing continuous insulation on the opaque. Here's the building in construction, obviously, but continuous insulation that is added onto the opaque parts of the facade. And you can see here that the glassy surface is quite limited, but tall windows, we want to get daylight back in, glass where it matters. And the last example, which is in design, is the California College of Arts. This is a project in San Francisco by Studio Gang. We continue to work on this project. This project, for those of you know where it is, California College of Arts has a campus in Oakland. This is downtown San Francisco. Here's the Bay Bridge, and Oakland is just right across the bay here. They wanted to move all their facilities from Oakland to San Francisco, and they have a site just in towards the south of the city, which they aspired to be net zero energy in the beginning. So, you know, we were brought onto this project really early on. We thought, oh, net zero building, totally can do it, no problem. We have this down, we got it. This is also a mass timber project, so it allows us to also tackle embodied carbon emissions. Went back to the drawing board with our first principles. How can we first condition this building using the first principles? So the project consists of these two building masses, and then a podium which has a few openings strategically placed to facilitate natural ventilation underneath it. And there are a lot of functions underneath this podium as well. So, you know, we designed for interior and exterior shading to deliver, again, on the same things that we are talking about, the experience piece, the solar control, the carbon emissions, passive cooling, going back to the board with the basics, use full daylight into the space, all the good stuff. And then we realized that this is California College of Arts. They have a huge process load that is electric furnaces. They do all sorts of cool glass blowing, cool art things there. And that is the need of the program. So although we can fantastically design a net zero energy building, what are we going to do with the process load? We can't really make any changes there. They also had a very specific selection of these furnaces that we really couldn't change much. And that's where we had to get creative about how we are going to actually tackle carbon emissions for this profile. So an academic building, so if this project did not have the makerspace that it does have, its energy use intensity would be 21. Just the makerspace, the activities, the process going on in this makerspace has an energy intensity of 32. And you can see the distribution here. Like 60% of that energy use is the makerspace. After we made this building really efficient and we got everything down, you know, the rest of the building energy use is the academic building, but we still have a massive chunk to deal with. So that's where we came up with this strategy that, you know what, we can cover not just our project, but also the adjacent building with PVs. But even that is not going to be sufficient PVs on the roof for us to be able to tackle carbon emissions. And this is not very new for any urban projects. On urban projects, the sites are restricted, the roof area is limited, the roof is also occupied by a bunch of things. You cannot put a lot of PV on it, and that PV is not going to be sufficient for you to get to net zero energy, let alone net zero zero carbon emissions or carbon neutrality. So what we did for this project as a result of this, also thanks to one of the donors on this project, who was extremely interested in this topic and wanted us to really tackle it, was we looked at the PV production on our site. We had already tackled the carbon emissions with good design, passive design, good active systems. That was taken care of. And then we had limited PV resources onto the building that were just not enough to get to carbon neutrality. We then added 2 strategies that have now become quite fundamental to design of buildings in California, which is energy storage. And the third one, which is a controller logic, which is still a new technology that we haven't seen a lot of projects undertake, but we have been working on more and more projects that allow us to do that. So what does all of this do? So if you remember the carbon emissions profile that I had shown earlier, which shows that there was this like smattering of reds and yellows and greens. What we wanted ultimately to do is for our PVs to only provide us electricity when the grid was red bad. When the grid was the worst performing, that is when we wanted the PVs to give us electricity. Now, that's not how PVs work. They only work when the sun is in the sky and when it is clear. So the battery allows us to store that energy, the PV energy, into the battery and allow us to deploy it at the right times of the day. And the controller logic, which is essentially a program that can be written to read the grid signals and then to feed that into the battery to tell that battery on when to get the grid, when to get the electricity from the grid because the grid is green, or when to get the electricity from the battery because the grid is red. And so once we add that intelligence into the building that allows us to deploy our renewable energy resource flexibly at the time that we want, only then are we able to take the project to carbon neutrality. So what we found on this particular project is that it was extremely essential for us to tackle the loads on the building because we have this finite resource of PV. So we had to really work on getting the building extremely efficient, deal with the loads as passively as possible, have good daylighting, have good massing onto the building, and then wisely utilize the PV panels in using a combination of batteries and the grid controller logic. So together, all of that allows us to get to carbon neutrality for this project. One of the other things that I wanted to just plant a seed here is that we see is like absolutely coming, and we expect that products like these will become available not very far from future, is renewable hydrogen. And it gets to that same question that we've been talking about in this presentation on what are the technologies out there that are going to give us the flexibility that we want for a changing grid. And the renewable hydrogen, basically what it does is, because you have only so much PVs that you can fit on your site, you can utilize that, that PV to essentially split water into oxygen and hydrogen. And that hydrogen then can be a stored fuel that powers a fuel cell that can be deployed at any point in time for your building. So we've seen a lot of startups and a lot of technologies out there that are packaging these steps together so that there is a deployable plug and play type of a hydrogen system that can be added to your PVs, and that allows you to flexibly control carbon emissions of your buildings. But that technology is definitely not mainstream yet, but just wanted to share what we are seeing as upcoming technology. And with that, I think that is all I have. I believe we have a few minutes for questions.
Yeah, it looks like we have 10 minutes left, so that's terrific. Thank you.
Okay.
I see Andy put a question in the chat. Fabulous presentation. Are you seeing an increase in cost in using materials with lower embodied carbon, e.g. paint and carpet? How much should we add into our cost estimates?
Right. So no, I am not seeing a higher cost related to lower embodied carbon materials at all. I think what I am seeing is a change in the process. I think we are talking to material suppliers as soon as like SD. We are having contractors onboarded very soon in the process, and we are starting that conversation way sooner than ever before. So I think that is changing. I think the products are out there. What often happens is that designers or engineers do not know how things are going to get bid and what is out there in the market to be able to like specify exactly that. So I think bridging that gap as quickly as possible, as early as possible, is what we are seeing as the most effective way to tackle this without any additional cost. I'm sure there are like costlier products out there, but we don't believe that that's necessarily the right answer. I think just having knowing what are the drivers for your project? Is it paints? Is it steel? What are those drivers? Knowing those, and then having the ability to contact the suppliers and understanding what range of emissions reduction is possible for those categories, I think we find more impactful.
Building on that, I see a question from Michael. Do you have any experience with urban mining and using used materials at a large scale?
Used materials, as in like salvaged materials? Interesting. So no, not particularly, but that is like super fascinating. I think I would like go back to that life cycle stages. Mining somehow makes me think that it is very energy intensive. However, I don't think that is the intent of this question. I think they're asking about recycling materials from the urban environment. So if that is where we are going, then I think that is going to, like I said, if you just like look at the material life cycle, the extraction process, the manufacturing process, and the assembly process, and then transportation also obviously, are the most energy intensive. So if you are getting rid of those, and if you're able to reuse whatever products that you have pretty easily, I think that is great. Now, one thing I'll tell you that we did look at, for a project, we were looking at railway tracks and looking at steel from railway tracks to be utilized into buildings. And what we found for that particular project is that I'm sure I'm butchering the terminology here, but essentially remelting or not like completely remelting, but for it to get upgraded to a building structural quality steel required immense amount of processing that then didn't make sense for those railway track steel to be utilized for building structure. Now, whether or not that steel could have been utilized for some other element, maybe make benches out of it, or make exterior shading, or maybe even cladding out of it, I think, yes, I think totally possible. But I think the gist of it is that, yes, reusing, recycling, great idea, but asking the question on what is the process to get the product from A to B, I think is the question that needs to be asked to make sure that we are not mistakenly adding to the emissions in this process.
Any personal experience, Michael, in having used materials?
No, that's why I was asking the question. I mean, there are some architectural offices, especially in Belgium and the Netherlands, that build their whole business model around being able to take elements from buildings that are being demolished, so then basically deconstruct rather than demolish those and use them in other buildings. I haven't seen it much in the US as much as it is in especially Belgium and Netherlands. That's why I was curious about your experience here.
Yeah, no, totally. And I think deconstruction is something that you're absolutely right. I think that is a lot of value, because what that does is that sets up the material to be recycled and to be reused, because you are almost like thinking through that next life in this life of the material. And I think that piece is quite important for that successful transition. And yes, I think we should be doing that, whether it is through modular construction, whether it is through not treating the materials as much so that, they retain their original form and properties that can be then easily adapted. I think all those strategies are, I think great strategies.
Yeah, and the other point with that is also the material paths, the idea of having exact information, data information of every material piece that you use in the building and how they are connected would be the next step.
Right, for sure.
I see a question from Mark. Do you evaluate different types of PV for embodied carbon, and are there significant differences between different panels, or are they all about the same?
No, they're not all about the same. They're very different. And yes, PVs, we've done embodied carbon calculations for PVs as their systems also, depending on where they're manufactured. So let me give you an example. So when PVs, let's just like unbundle that a little bit. When you think of PVs, you're thinking about the extraction of the silicon and the actual material. You're also thinking about the framing and all of it. Now, all of these are like metal or metallic materials, and they are very energy intensive to be mined and to be assembled. Now, if that assembly and if that mining is happening in a grid region that is all coal-based, then that is going to lead to a very high embodied carbon emission of that product. If that mining and if that assembly is happening through facilities that are powered by PV, I don't know, I don't think such a facility exists, but if it was that the case, then the embodied carbon emissions would be very low. So where that's coming from and how that is being put together makes a huge difference. Now, on top of it, now, if you think about like BIPVs as an example, like the first example that I just gave you was, let's say we are comparing the standard PV panels, the blue, gray, black looking ones to each other. Now, if you're comparing between systems with a PV panel to a building integrated PV panel that maybe has some PV printed on a glass, then that's a completely new sort of material profile that you need to look at to see whether that is carbon intensive or not. But the gist of it is anything, I would say, that is like a lot of metal and a lot of assembly, any products that require a lot of assembly and have a lot of metal typically are very mining heavy and also very electric grid heavy. And if they are all done in a place where the electric grid is coal based, then that is going to be very high emissions.
As a follow-up, do you see that programs like one-click LCA or other various softwares that allow you to calculate out your embodied carbon already have that level of information? You could get to that level of data picking, I want this solar panel and here's my coordinates, and it'll give it to you.
Yeah, I don't think so. I don't think that exists in OneClick or any of the databases. I think where we have done this is by contacting suppliers directly and like working with them and doing that research. Even like systems like the aluminum comparison that I had in the presentation, even that level of information is not in the publicly available databases right now. So it is, I think it's like changing very rapidly, but when it is still requiring a lot of research and calculations of specific products. I think what is available in the publicly available databases now is, some basic information on concretes and steel and a lot of other products too. I think it was like just not there, and I'm very glad that that database now exists for at least like common products.
And what about with the considerations for, say, using mass timber, comparing that to steel as a primary structure, and right. Where, I don't think there are too many sustainably forested forests nearby to California yet, right? It's Pacific Northwest or
right.
Or east, like Alabama or something.
Right.
And in which case you're trucking pretty far.
Yeah. So a couple of things there. One is that sourcing. I think you said it right. Sourcing is extremely important for mass timber. So any timber, I don't think is a good idea. Or I think it needs more thought than that. Sourcing is important. I think where we see a difference is if the carbon that has been sequestered by the wood, if that is, or by the timber, if that is locked into the building, as in so when you basically cut down a tree and you are, even if it is FSC certified and like sourced properly, the tree was actively sequestering carbon. So there's like carbon locked into it. Now you got to figure out a way to preserve that tree or that element, that timber element, for a very long time, so that that timber element doesn't become compost, because once it goes back to the ground, it is going to release all that sequestered carbon into the atmosphere. So it is important to be able to design timber structures for disassembly, for reuse, and to prolong its life as much as possible without just thinking that it's just timber, so obviously very little carbon emissions. So there are both aspects to it. Sourcing, I think rightfully sourcing it is an important aspect, because you don't want to be creating one problem while solving another. There are many other biodiversity and ecosystem related issues. Old growth forests are a big no. So I think really being knowing where that timber is coming from, and then making sure that the carbon that is already locked in can continue to be locked in.
Do you have a sense of how long that time period would be for it to need to be used?
No, it depends on, No, I mean, there are, I don't know what happened. My camera went away, but
Oh, no problem. And we've got more and more questions coming, so sorry, I'm hogging.
Oh, no worries about that. I think that's because my, I'm just going to move to my desk. My battery is dying, but I'll continue to talk. So
Oh, that's no problem.
Essentially, no, we don't know, and it changes. I mean, there are timber structures in the world that are centuries old. So clearly it can be done now, whether that can be done in high rises, whether that can be done in laminated timber, whether that can be done in modern surfaces. I do not know the answer to that. And I don't think I've actually looked into it. So I don't have a clear answer for that. Sorry.
No problem. I see a question from Andy again. How much do you use automation versus user control for operable windows and night flushing, etc.?
Depends on the client. For night flush, if the question is specifically for night flush, then I think automation works really well. For night flush, the system has to be designed for night flush. But I think it's pretty straightforward and easy, and I think it works really well. For opera windows in general, we've had clients where they believe keeping it simple is the best way to do it. They also believe in giving control to the occupants. And I think that makes a lot of difference, and it honestly does. So I think it depends on what space you're trying to design this strategy for. If it is a space like it was for Uber, where there is no sort of like owner of the space, then, that level of automation, and again, it was like trying to do something very different, then I think that level of then automation makes sense. If it is like office space, like I am sitting in right now, it's great to have an operable window right next to me. I think it is way more effective. I would be very unhappy if it was automated and if I'm sitting next to an operable window and if I had no control over it.
I see Kara is wondering what programs are typically used for modeling and facade analysis.
Modeling facade analysis, the daylight analysis, or
which ones do
that
you
radiance?
And then Mark was wondering, do you think that using blockchain protocols could help track materials embodied carbon if there was a widespread adoption?
Which materials again?
For tracking materials embodied carbon.
Oh, blockchain protocols. Oh, that's very interesting. I don't know. I have not thought of it, but please tell me, what is blockchain protocol?
Either. So Mark, you want to weigh in on how that might be utilized? Are you still on the?
Yeah, sure. Sorry, I know I look like a ghost, but
oh, it's all good.
Well, I've just, and one of the things is verification, right? And like having a sticker on a material that kind of says, here's where it's from, here's the, blah, blah, blah. But that is always subject to, it's hard to verify. And I just wondered if, if materials started being sourced and tracked, using blockchain, then there'd be a verifiable. It's kind of like what do you do for wood at Forest Council, right? That certification. Yeah. It would be like a built-in certification, which would be awesome.
Yeah. And honestly, you know what? I think it is gonna. I think it's gonna come. I think it is gonna happen. The embodied carbon world, I want to say, like barely existed 5 years ago, like in terms of how you're actually utilizing it on projects. And it has like made so much progress in the last 5 years. And I think it is just getting started. I think there's so much awareness around it right now. And I'm not just like talking from I know the world is going to make it perspective, but also, you know, on the other end, the material manufacturers are under pressure like no other time to deliver on some of these criteria, not just because clients are asking it, but because ESG criteria in general have taken so much prominence in the corporate world. So I think it is like becoming this whole conversation from materials manufacturers, which was more of a nice to have thing from material manufacturers, that is changing because it has now become a boardroom conversation for material manufacturers. So I think that is also changing like never before. So I think regulation and I think it'll come, or so is my hopeful mind saying so.
Thank you.
Well, I think we're far over time because that was such an exciting presentation. We have lots more questions for you, but we should
yeah, if you I can put my contact information here. Please contact me. I can keep on talking about this forever. This is what I do, and I do it very passionately.